This is the second video for section 4.5 out of the OpenStax Calculus 1 textbook. In this video, we will be looking at concavity and inflection points and the second derivative test. This will be a briefer video since there is in some ways less material to cover. In the last video, we looked at the first derivative test, which can tell us where a function is increasing and decreasing, and it can tell us where to look for the relative extrema. Concavity tells us where the function is curved upwards or curved downwards. We saw these when we were looking at the graphs of position, velocity, and acceleration with respect to time. Now we see them in situations that are not directly linked to some sort of physical real-world meaning. In order to apply these, let's review the formal mathematical definition for concavity. Supposing that a function is differentiable over an interval means that the function must be continuous over the interval, since if you are differentiable, you are also continuous. Providing that we have such an interval and the first derivative is increasing, we say that the function is concave up. That means concave up is curved up like a cup, as in this section right here. That means that the second derivative is greater than 0. Over here, in the second box, you will see that the second derivative being greater than 0 implies that the function is curved in an upward manner like a cup. If the second derivative is negative over a particular interval, then that means that the function is curved down over the interval, or what we say concave down like a frown. Up like a cup, down like a frown. These two mnemonics will help you remember which way is which. Up like a cup implies that a cup, of course, is shaped like this, with a handle off to the side. Down like a frown is in reference to a smiley face with a frown on the face. That means it is curved downward. Let's look back at the original function we had in section 4.5 and think about the concavity. We still have the first derivative on here, and we notice that at this point, the first derivative is positive because it is going uphill. In the next section, the first derivative is negative, which indicates that it is going downhill or decreasing between A and B. Then it is increasing, first derivative is greater than 0, all the way from B to C, and again from C to D. That is because there was a saddle point at C. The first derivative to the right of D is decreasing, which means it is negative since it is going downhill. Now let's look at concavity and see if the concavity can help us figure out where relative extrema might occur as well. When we're looking at the first region between negative infinity up to A, we can see that in general it looks like this part of the graph is curved up like a cup. This must mean that the second derivative is positive in that region. On the other side of that critical point at A, we see that between A and B, the function is also curved up like a cup. That means that the second derivative is still positive there. In other words, at that critical value, on both sides, we have an up like a cup. On the next critical point at B, we can see that on both sides of that, it is curved also up like a cup. In fact, we can see that the second derivative is not changing sign really until we get somewhere in this region right here. Somewhere around here, it changes from up like a cup to down like a frown. In this section, the curvature of the graph is definitely down, which means in here, our second derivative must be negative. On the next section between C up to somewhere in this vicinity, we again have an upward curving graph. Here we must have the second derivative being positive, but as we approach the top, notice that it has gone negative again. On the other side of the hilltop, it looks as though it has staying curved downwards forevermore. That means that the second derivative stays negative as it is concave down forever to the right. This makes it clear that the curvature is definitely not changing at the critical points, that in fact the curvature is changing at what we called inflection points when we did this previously. In order to determine where the curvature changes, we will need to find these inflection points. Before we get there, is there anything about the second derivative that can tell us where we might have a relative maximum or a relative minimum? Looking at the two on the right side, if we look at the relative maximum, actually the absolute maximum, occurring at x equals d, we can see that it is curved down on both sides and that at d we have a relative max. At b, we can see that it is concave up on both sides, or the second derivative is positive and we have a relative minimum. We will make a temporary theory that when it is concave down and we have a critical point, that we must have a max, and when it is concave up and we have a critical point, it is a relative minimum. It is not clear yet what will happen at a cusp where the first derivative is undefined. If the first derivative is undefined, then clearly the second derivative is also undefined. Let's move on and look at the next section. Here we see the formal mathematical definition for an inflection point. The inflection point is defined when the function is continuous at that point, but the function changes concavity there. That means it changes from being concave up to being concave down, from curved up like a cup to curved down like a frown. When we were looking at position, velocity, acceleration graphs, we had to guesstimate where we thought these occurred. We will now be able to compute them exactly. Looking at the graphs, again, what we are looking for are those values where it appears that somewhere in the graph it changes from curved up to curved down, probably in here, somewhere around in here, and again, perhaps somewhere in here. In those regions, it changes from being curved up like a cup to down like a frown, up like a cup, down like a frown, and up like a cup. On the second graph to the right, we have a cusp in the graph occurring when x is 0. Notice that we have a curvature which is concave up on the left of the cusp and concave up on the right of the cusp. Notice that this does not change and does not occur in the graph on the left. On the left, we are clearly going from concave up to concave down, to concave up, to concave down, to concave up. We do not have two sections that go concave up, concave up. It could be, and we will need to determine, if the presence of the cusp is what allows it to be concave up on both sides. And in fact, we'll see that this is the case. Normally, without cusps or corners, the concavity will go from up to down to up to down and so forth. Let's look at two more graphs. Looking at these two graphs, I can see that the one on the left is concave down until it reaches somewhere around in this vicinity where it changes to concave up. But here in this section right here, it must be concave down, so I must have another inflection point here. It is not clear what's happening in this region just to the right of 0 because the graph is so small there, I cannot see the change in curvature. I suspect that it must have another inflection point in that region. This brings up a really important point. Some graphs, the change in curvature is so minute and so small that you cannot see it with the naked eye. But with algebra and calculus, you can know that it must be there. This would also definitely changes curvature again somewhere over in here. The graph on the right does have a cusp occurring when x equals 1. Let's see if the curvature changes this time on either side of that cusp. On the left, it appears to be concave down, but on the right, it does look like it's concave up. In other words, it is not required that it stay the same curvature on either side of a cusp or a corner. It could change, but it does not have to. In the first picture on the right, we see that we had a cusp, but it remained concave up on both sides. In the second picture on the right, we see that it changed on the left from concave down to concave up on the right. We will have to be able to determine this directly using algebra and calculus. Let's approach an example and analyze where the inflection points are and where it is concave up and concave down. This is preparing us for section 4.6, where we will use all of this information we've gathered in section 4.5 to draw an estimate of what the graph looks like, predicting where it is increasing, where decreasing, where the relative maxima are, where the relative minima are, where it is curved concave up, where it is curved concave down, where the inflection points lie. Let's look at that example. Here's example 1. Let's take a look at this function and find out where it is concave up, concave down, and where the inflection points are. To find an inflection point, we know that the second derivative has to change sign, or it has to be 0 there. So an inflection point is where it changes from one to the other. When we're looking at this, the first thing we need to do is take the derivative of the function. When we do that, we also need to consider what the domain of the original function is. Anything not in the domain cannot be either a critical value for the first derivative or an inflection point for the second derivative. In this case, when we look at the domain, we know that natural log can only accept values from open 0 to infinity. However, if x is squared, it will definitely never be negative. Is there any value that would cause the 3x squared plus 1 to be 0? There's not. This means that the domain of this function, even though it is natural log, is actually all reals, or negative infinity to positive infinity. Every x value you plug in there will give you a strictly positive number. That means that any value I find for the first derivative is a possible critical point, and any value I find for the second derivative is a possible inflection point. Let's find the inflection points now. To find the inflection points, I need to know where it changes from concave up to concave down, or vice versa. To do that, let's analyze the second derivative. First, we find the first derivative, and the derivative of natural log is 1 over u du dx. 1 over u is 1 over 3x squared plus 1. The derivative of 3x squared plus 1 is 6x. This leads to the first derivative being 6x divided by 3x squared plus 1. Now let's find the second derivative. The second derivative is the derivative of the first derivative. In this case, I will use the quotient rule. That gives me the denominator, 3x squared plus 1, times the derivative of the numerator, which is 6. minus the numerator, 6x, times the derivative of the denominator, which is 6x as well, all divided by the denominator squared. As before, we will leave the denominator in its squared factored form. To simplify the numerator, I multiply out everything and apply algebra. This gives me 18x squared plus 6 minus 36x squared, divided by the denominator squared. When I reduce this, this is going to give me a negative 18x squared plus 6 divided by the denominator 3x squared plus 1 quantity squared. Now I need to know when the second derivative changes sign. I'm going to use a similar technique to what I used for analyzing the first derivative. This means I'm going to write my second derivative in a fully factorable form and analyze the signs. This time, just to show you that it can be done, I'm going to further factor the numerator by factoring the negative 6 out of the numerator. That would leave behind a positive 3x squared minus 1. If I redistributed, I would get back to negative 18x squared plus 6. And again, we do nothing to the denominator other than leave it in its factored form with the square outside. Now I have 3 different factors in this version of the second derivative. Let's outline the 3. Negative 6 is one of the factors. The quantity 3x squared minus 1 is a binomial factor, and 3x squared plus 1 is another binomial factor, which is being squared. Let's make one row for each of our 3 factors, and we will choose test points. This time, we are not evaluating the first derivative, but instead are looking at the second derivative to determine concave up and concave down. I will make one number line for each factor, and I will include one for the second derivative as well. Now, in order to know where these go, I need to know when the second derivative is 0 or when the second derivative is undefined. When would the second derivative be 0? That would occur whenever the numerator is 0. The numerator will be 0 whenever 3x squared minus 1 is equal to 0. When that is 0, the second derivative is 0, and this is the most likely place to find an inflection point. This is going to give me 3x squared equal to 1, or x squared equal to 1/3. Taking plus or minus the square root gives me 2 values to consider, plus or minus the square root of 1/3, or plus or minus 1/the square root of 3. You can also write this as square root of 3/3 if you prefer. That means on my chart, I will need one vertical bar for the negative 1 divided by the square root of 3, and another vertical bar for positive 1 divided by the square root of 3. If my second derivative changes sign, it must be there. It cannot happen at any of the solutions of the denominator because the denominator is squared and must always be positive. Now I need to take a look at the signs produced by each factor. I know that negative 6 is a negative number and will stay negative no matter what my test point is. I haven't chosen test points, so let me go ahead and choose those now. I don't know exactly what negative 1 over the square root of 3 is, but I know it has to be less than 1. So choosing -1 is a safe bet for being to the left of that number. Between -1 over the square root of 3 and 1 over the square root of 3, I would probably choose the test point of 0. To the right, I would choose a test point of 1. Now I'm going to plug them in to the remaining factors and see what I get. When I plug in -1 to 3x squared minus 1, the negative becomes a positive when I square it. That gives me 3 minus 1, which is 2, which is definitely a positive. When I plug in 0, however, the first term drops out and I get -1. That makes it negative. When I plug in 1, notice that because the x was squared, I get the same thing I got when x was -1. That means that it must be positive in that region. The third factor corresponding to the denominator is squared, so it is positive in all cases. Combining the signs in the fraction gives me a negative over the region from -infinity to -1 over the square root of 3, a positive between -1 over the square root of 3 and 1 over the square root of 3, and a negative again between 1 over the square root of 3 to positive infinity. Let's interpret what this means. This means that over the region from -infinity to -1 divided by the square root of 3, my graph must be concave down. We typically will abbreviate concave with CC. That means it is concave down over that interval. It's also concave down over the interval from 1 over the square root of 3 to infinity. It is concave up then only between -1 over the square root of 3 and 1 over the square root of 3. That means that we have a change in curvature at -1 over the square root of 3 from curved down to curved up. That makes that point an inflection point. We have another inflection point at +1 over the square root of 3 because it goes from curved up to curved down. How do we find the coordinates of these inflection points? To find the coordinates, we need to plug in -1 over the square root of 3 and 1 over the square root of 3 into our original function. Just to remind you, the original function was f of x equals the natural log of 3x squared plus 1. To find the inflection points, I need to take each of those values and plug them into the original. F of -1 over the square root of 3 becomes the natural log of 3 times -1 over the square root of 3 quantity squared plus 1. Notice that because it's squared, I'll get exactly the same value coming out of 1 over the square root of 3. When I plug these in, -1 over the square root of 3 squared will give me 1/3. That gives me natural log of 3 times 1/3 plus 1. 3 times 1/3 is 1, and 1 plus 1 gives me 2. That means I have an inflection point at -1 divided by the square root of 3, natural log of 2, and another inflection point at 1 over the square root of 3, natural log of 2. That is where you will find the two inflection points on this curve. Now let's consider the formal statement of the second derivative test. The second derivative test says that the first derivative is 0, which implies that C is a critical point. In other words, this first condition that you see here means that C is a critical point, and the critical point came from setting the first derivative equal to 0. If that's true, and the second derivative is continuous over the interval containing C, and that means you have to be able to draw it without picking up the pencil, then we can make the following conclusions. If the second derivative f double prime is greater than 0, meaning it has to be curved up like a cup, then C must be a local minimum. If the second derivative, f double prime, is less than 0 or negative, that means it's curved down like a frown, and that means the function has to have a local maximum there. There is a third case for the second derivative test, which is, what if the second derivative at that critical value C is 0? If that happens, the test is inconclusive. That means we cannot tell what happens, and in that case, we have to revert to the first derivative test, analyzing increasing and decreasing to determine whether or not we have a relative extrema at C. This brings up a good point that you need to consider when analyzing graphs. The first derivative test is sort of your quadratic equation of using derivatives to analyze graphs. The first derivative test always works and never fails. The second derivative test is shorter and less work, but like factoring to solve a quadratic equation, it does not always work. If you get that the second derivative at a critical point is 0, then you will have to revert to the first derivative test. Let's take a look at an example. How can I apply the second derivative test to the graph of the function x to the fourth divided by 2 minus 12x squared? In your first step for all of these, you should analyze the domain of the original function. In this case, because it is a polynomial of degree 4, my domain is all real numbers from negative infinity to infinity. Any critical point I find is possible for the location of a relative extrema. Any second derivative value equal to 0 is a possible place for an inflection point. The second derivative test is like a shortcut that doesn't require you to analyze increasing, decreasing, or concavity to determine whether or not you have a relative extrema. The second derivative test says, is your function defined over the interval, and looking back, do you have critical points, and is the second derivative continuous over that interval where the critical point is? In order to apply it then, we need the critical points. To find the critical points, we need the first derivative. The first derivative equal to 0 gives us one possible location of the critical points, places for relative extrema to exist. The second possible place for critical points is the first derivative does not exist, but the function does. First, we'll find the critical points from the first derivative equal to 0. Applying the power rule to the original function, for the derivative, I come up with the formula 4 over 2 x cubed minus 2 times the 12 x to the first. If I rewrite this in a better form by simplifying it, I can get that this is 2x cubed minus 24x. If I look at this, I know that I can set this equal to 0 and solve for where the first derivative is 0. I can factor out the 2x that is a common factor, and that leaves x squared minus 12 behind. One possibility is 2x equal to 0 or when x is 0. The other possibility is when x squared minus 12 is 0, or x squared equals 12, or x is plus or minus the square root of 12. Writing 12 as 3 times 4, the square root of 4 is 2, so I get plus or minus 2 square roots of 3 from algebra. That gives me 3 critical points from the first derivative equal to 0. That would be at 0 and at 2 square roots of 3 and negative 2 square roots of 3. The other place that I could have a critical point would be when the first derivative does not exist, but the function does exist. In this case, my first derivative was itself a cubic polynomial, 2x cubed minus 24x. It is defined for all real numbers, so there is no place where the first derivative does not exist, but the function does. That gives me no additional critical points. I am not going to find where it's increasing, decreasing, concave up, or concave down. What I'm going to do now is a simple shortcut to go right to the heart. Where is the relative extrema? This is going to be when the second derivative test works. For the second derivative test, to remind you, we will plug the C value, the critical point, into the formula for the second derivative. If it is positive, then it is concave up, and there's a local minimum at C. If the critical point in the second derivative is negative, we have a concave down and a local maximum. If we plug the critical point into the second derivative and get 0, we'll have to go back to the first derivative test. Let's take a look at the second derivative now. To find the second derivative, I will go back to the non-factored form of the first derivative, which is here next to the check mark. To find the second derivative, I will apply the power rule again, which will give me 6x squared minus 24. I'm not analyzing concavity this time. I'm simply going to apply the second derivative test. For me, this means plug the values 0, 2 square root of 3, and negative 2 square root of 3 into the second derivative. If I take 0 and I put it into the second derivative, I get 6 times 0 squared minus 24, which is negative 24. That means it is negative and concave down, which means that I have a relative minimum, or maximum rather, at the critical value x equals c, or 0, our c value. I won't know what it is until I plug it into the original function. The original function can be found up above, x to the 4th over 2 minus 12x squared. So if I plug that into the original function, x to the 4th over 2, hang on while I get a different marker, maybe will work a little better. X to the 4th over 2 minus 12x squared, and I plug in 0, I'm going to get 0. I have a relative maximum of value 0 occurring at x equals 0. Now let's plug in the other two critical points into the second derivative to see if they are also relative extrema. Plugging in 2 square roots of 3 into the second derivative, I get 6 times 2 square roots of 3, quantity squared, minus 24. Squaring that will give me 6 times 2 squared is 4, square root of 3 squared is 3, minus 24. 4 times 3 is 12, and 12 times 6 is 72. 72 minus 24 is definitely a positive number. That means it is concave up, so I must have a relative minimum occurring at the critical point x equals 2 square root of 3. To find the value of the relative minimum, I have to plug 2 square roots of 3 back into the original function found over here at the left. That would give me f of 2 square roots of 3 equal to 2 square roots of 3 to the 4th power divided by 2 minus 12 times 2 square roots of 3 quantity squared. If I apply this, what will I get? Continuing the algebra, I have 2 to the 4th is 16. The square root of 3 times itself 4 times would give me 9, all divided by 2, minus 12 times 2 squared is 4, square root of 3 times itself is 3. 16 over 2 is 8, and 8 times 9 is 72. And 4 times 3 is 12, and 12 times 12 is 144. This gives me a value of negative 72. That means that my relative minimum value is negative 72 occurring at 2 square roots of 3. Because the powers in the original function were both even, I would get the same values if I plugged in negative 2 square root of 3, which is my other possible point, my other critical value, which means that this one is somewhat symmetric. That means that I have another relative minimum occurring at x equal to negative 2 square roots 3 of value also negative 72. Now let's take a look and see how we did. On the left, you'll see that I have inserted a graph of the original function x to the 4th over 2 minus 12x squared equals 0. Do we in fact have a relative maximum that we found to occur at 0 of value 0? Yes, we do. The relative maximum is at 0, 0. Do we have two relative minimums, both down at negative 72, occurring at x equal plus or minus 2 square roots of 3? And in fact, we see that we also have those values on the graph. Again, the second derivative test is best when you get a value other than 0. If you get 0, then you cannot use the second derivative test and will have to revert back to the first derivative test. Let us take a look at one last example for this video. This example is x cubed minus 6. If I'm looking at the graph of x cubed minus 6 and I want to know where the relative extreme is, the question is, can I use the second derivative test? To apply the second derivative test, the first thing I would like to do is analyze the domain. Make sure that all the values you're looking at are in the domain of the function. As a polynomial, the domain is all reals, so I have no restrictions. Now I need to find the first derivative to get the critical points from f prime equal to 0 and the second derivative to plug them into. The first derivative gives me 3x squared minus 0, or 3x squared. The first derivative, to find critical points, I only want to look at the ones coming from the first derivative equal to 0 for the values where the second derivative test can be applied. In this case, I'm looking at 3x squared equal to 0, which occurs when x is 0. That's my only critical point. In fact, this one has no other critical points because the first derivative is defined for all x. Now I find the second derivative. The second derivative, applying the power rule again, would be 6x. To apply the second derivative test, I will take the critical value found from setting the first derivative equal to 0 and plug it in to the formula for the second derivative. In other words, take your formula for the second derivative and replace x with the critical point from the first derivative. This is 6 times 0, but unfortunately, that's 0. That means the second derivative test failed to work, or what we call inconclusive. That tells me nothing. I don't know what happens at the point where x is 0. To determine it, I will have to go back and look at the first derivative test. The first derivative test I will take and I will analyze. Since I only have one factor, I can look at the first derivative test by analyzing 3x squared. It only has one critical value at 0. To the left, any negative value, if I plug it into 3x squared, will still be positive, and same on the right side. This means that my first derivative must be increasing in all places. What must be happening at 0 is I must have a saddle point on the graph. And in fact, that is precisely what occurs. There is a saddle point in the graph of the original function when x is 0. The original function is x cubed minus 6, which if you sketch the graph is going to be crossing the y-axis at -6, but otherwise is the cubic function. We do have a spot right here when x is 0 where the tangent line becomes horizontal. That means the first derivative is 0, but it is not an extremum value because it is neither a local max nor a local minimum. In this case, the second derivative test failed to work, and we had to revert to analyzing increasing and decreasing to find the relative extrema. This is the end of the second video over section 4.5.